All right, you guys, we're going to get started today on polynomial functions. All right. The most confusing part of the day is going to be notation, just because there's going to be a lot of letters, a lot of variables, a lot of powers, a lot of coefficients. And I mean, it's very confusing to look at. But the concepts we're going to go over today shouldn't be super challenging. Okay. So we're going to get right into things. We have polynomial functions, all right? And this right here is the general form. Again, obviously notation looks really confusing, but all this means is a sub n is some sort of coefficient, and then we have x to some power. And then we have, so I'm going to make sure that's an example. Then we have a new coefficient, so maybe like 3, and then we have x to a power that's less than that, or 1 less than n, okay? And then we continue on dots, and then we have, 2x, and then a sub 0 is just a coefficient, okay? There's no variable tied to it. So you can see all it is really confusing notation for a lot of us, but it just is a coefficient, a variable with some sort of power, okay? So if you look at the table below, we have names of polynomials. So we have constant, linear, quadratic. Those are 3 types of polynomials we've talked about. The new one's going to be cubic and quartic, or that's degree 3 and degree 4. And then we obviously have our general form below, okay? So remember, I mentioned it yesterday, or on yesterday's lesson, or 5.2 rather. The degree of the polynomial is going to be that highest power associated with your expression. So in a constant expression, my highest power is 0, which means the degree is 0. The leading coefficient is the coefficient of that highest power term. In this case, it's 12. Thus, with a linear expression, my degree is 1. The leading coefficient of that power is 4, right? Quadratic expression, the degree is 2. The leading coefficient of that power is 5. In a cubic function, the degree is 3. The leading coefficient is 8. And generally, the highest power in this case is n. The leading coefficient is written a sub n. Again, don't let the notation confuse you, but polynomials are always going to be in this form, and typically we're going to list it in standard form from highest to lowest power. So the first part of the day is identifying some polynomials, okay? And if they are a polynomial, we want to state the degree and leading coefficient, all right? The only way I can make these problems are confusing or not write them in standard form, okay? So looking at this problem, hopefully you see your highest power is right there. Even though it's not listed first, it is the highest power. So yes, number 1, this is a polynomial. It's just not written in standard form. The degree of this polynomial is 6. 6 is the highest power in the expression. And then my leading coefficient is -4. That's the coefficient of that highest power term. All right, as we move on to example B, hopefully you notice here, we have a negative exponent. So this is not a polynomial. Just like we talked about on lesson 5.2, when we have negative exponents, those are not polynomials. Polynomials must have whole number powers to be a polynomial. All right. Looking at this next problem here, we do have a polynomial. All right. If you notice, our degrees when we add them together are 3, or we have 3. Remember, when we have polynomials of multiple variables, we want to take the highest sum of those degrees. All right. But if we go back to the directions, it says a polynomial in 1 variable. So this is not a polynomial in 1 variable, okay? If it was a polynomial in 2 variables, the degree would be 3, and then you'd have leading coefficients of 2 and 5, all right? Second part of the day is going to be looking at evaluating functions, all right, or evaluating polynomials. So we're told f of x is this polynomial x squared plus 2x minus 3. All right. If you remember back to function notation, if I just said f of 2, that would be 2 squared plus 2 times 2 minus 3. So we're just plugging in x to wherever we see an x. So we have 4 plus 4 is 8, minus 3 is 5. So the function's value at 2 is 5. We can do the same thing with algebraic expressions, all right? So in this case, I want to figure out the function's value at 3c minus 4. So what I do is I take 3c minus 4, and I swap that in for the x, all right? So I have x squared plus 2x minus 3. And that is going to be my function's value at 3c minus 4. I then want to subtract 5 f of c. So I'm going to do 5, and then f of c means I'm going to take c and plug it into my x's. So I have c squared plus 2c, whoops, not plus 3, minus 3. All right. So over here, we have minus 5c squared minus 10c plus 15. And then over here, we want to expand this. We'll need to FOIL my first expression. I wind up with 9c squared minus 24c plus 16. Now I can move on to the second and distribute. So I get plus 6c minus 8. And then we have that minus 3 off to the side. I'll want to combine like terms. So I have 9c squared. Looks like I have minus 18c. 16 minus 8 is 8. 8 minus 3 is 5. So then we have, that's my function's value at 3c minus 4. This is my function's value at c times a negative 5. Then from here, we want to combine like terms. So we have 9c minus 5 is 4c squared. Negative 18 minus 10 is negative 28c. And then 5 plus 15 is 20. So that is the value of that expression, okay? Again, be mindful of things. Take your time and do one thing at a time as you go through these problems. If you try to do too much, typically that's where you're going to end up making a mistake. Okay. Continuing on our exploration with polynomial functions, we're going to look now at graphs of polynomial functions. So a constant function should be pretty easy to remember. A constant function is something like y equals 2. Okay. A linear function is something like this. So maybe we have 1/2 x plus 1. Okay. Quadratic functions, we've also talked about. So they're parabolas. So we might have something like y equals x squared. These three graphs should be very familiar to you. Okay. The next three will not be as familiar. Okay. A cubic graph kind of looks something like this, right? And this would be x cubed, for example. Okay. A quartic graph has a degree 4 polynomial. All right. And with a quartic graph, all right, you can have a few different terms. Okay. So we could have something that looks kind of like a W as far as things go. And again, the degree of these is going to be 4. The last one will kind of generalize as a quintic function. And this one, as you may have guessed, is going to be kind of a little similar to the degree 4. where we have these bumps, okay? But in the case of a quintic function, they're going opposite directions. Again, degree of a quintic function is 5. So I'll kind of just let you digest all these a little bit. We have a constant, which is a straight line across. A linear function is a straight line. We have quadratic. Both sides are going up. A cubic, the directions are split. A quartic, the directions are the same. And a quintic, the directions are different. And that's actually what we're going to get into next, is what's called end behavior. So if you notice, with a linear function whose degree is 1, it goes down one way and up another. Degree 3 polynomial, it goes down one way and up another. Degree 5 polynomial goes down one way and up another. If you notice a degree 2 polynomial, all right, they match. They're either both going up or maybe they're both going down. And that's what the second part of the day is going to be, is generalizing this information. And what we call this is generalizing end behavior. There's a few different situations. We have odd functions and we have even functions. Okay. We also could have a positive leading coefficient and a negative leading coefficient. All right. Forgot even, negative. Okay. So our end behavior can be generalized as these 4 cases. All right. And again, the most confusing part about this is kind of writing down your notation as far as end behavior goes. Okay. So when we think about an odd positive function, I'm kind of thinking of the line y equals x. So we have a line like this. If I'm thinking of an even positive function, I'm thinking of a parabola that opens up. If we have an even negative, I kind of get the image of a parabola opening down. And if I have an odd negative, I'm thinking of a line that has a negative slope. And those are kind of the pictures I'm going to put in my head to help me describe our end behavior. And our end behavior is what's happening on the left side of my graph and what's happening on the right side of my graph. So as my x goes to negative infinity, that means as my x values go to the left, what is happening to my function? Is it going up or is it going down? You also want to state, as your function goes to the right, what's happening to your function's value? Is it going up or down? And this notation can be utilized. Sorry, I'm going to copy this over. Clone. And I'm going to clone it again, because this is never going to change for you. Okay? What is going to change is what you plug in. Okay? And this is where these pictures come in handy. So if you have an odd degree polynomial with a positive leading coefficient, as we move to the left, my graph is going down, or negative infinity. As my graph moves to the right, if you notice, I'm going up towards positive infinity. And that's how you'd state the end behavior of an odd positive function, any odd positive function. So if you said, I have the function 15x to the 47th power, this end behavior would match, guaranteed. Okay. Now we'll go into the next one. All right. Thinking about an even positive function. So we have an even positive leading coefficient. Both sides are going to go up forever. All right. So as we go to the left, my graph is going up. As we go to the right, my graph is going up. As we switch back to odd negative, we have that image of a line with negative slope. So as I go to the left, my graph is actually going up. As I go to the right, my graph is going down. And the fourth and final case, even negative. As my graph goes left and right, my function's value decrease forever, or they go down towards negative infinity. Again, our end behavior is always going to be one of these four answers. Regardless of how big or confusing your polynomial equation is, if it's odd, positive, it's always going to match. We'll call it case number 1. If it's odd negative, it's going to match case number 2. If it's even positive, it's going to match case 3. And if it's even negative, it's going to match case 4. Those answers will just change based on whether it's an even or odd function and whether it's positive or negative. Those four cases will never change. All right? So you can pause the video there or rewind if you need to, but we're going to go into this last example here. All right? So describing the end behavior of my graph. So that's what I'm going to do first. All right, notice our notation is the exact same. All right, as we go to positive infinity, what happens to my function's value? So this is part A. Well, as my graph goes to the left, it's going up forever. As my graph goes to the right, it's going down forever. All right. If you remember, end behavior that is different, goes up one way, down another, is always evident of an odd degree polynomial. Okay? The last question we're going to look at is state the number of real zeros. Well, if you remember back to chapter 4, our real zeros coincide with the x-intercepts of our graph. So on the problem 1, there are 3 real zeros on this graph. All right. Going back to part B. Oh yeah, just odd or even. I don't have to say if it's positive or negative, but if you remember, up to the left, down to the right is almost like a line going down. So we know the leading coefficient of that polynomial, whatever it is, would have to be negative. All right. Last situation here. All right, writing down our end behavior again. The notation does not change. We just have to fill those in. All right, looking at things, we go down to the left and down to the right. All right, so both directions are negative infinity. I didn't need to write a b again. What am I thinking? When our end behavior matches, that's indicative of an even polynomial. And since they both go down, we know the leading coefficient is negative. I know it doesn't say that, but we know that. All right. And then in this case, we know there are 2 real zeros to the graph. Your homework's on the bottom. Make sure you're actually doing the assignment that's listed on the weekly planning guide. I don't know. I think that's actually exactly it. If you have any questions, please let me know via Google Meet or the discussion board. And best of luck completing this assignment.